A metal rod of mass 0.22 kilograms lies across two parallel conducting rails that are a distance of 0.52 meters apart on a tabletop, and there's a 3 ohm resistor connected across the left end of the rails. The rod and the rails have negligible resistance but significant friction with a coefficient of kinetic friction of 0.2. There's a magnetic field of 0.8 Tesla perpendicular to the plane of the tabletop, and a string pulls the metal rod to the right with a constant speed of 1.8 meters per second. In Part A, calculate the magnitude of the current induced in the loop formed by the rod, the rails, and the resistor. So the motional EMF is given by B times L times V. The magnetic field is 0.8 times the length, which is the distance between the two conducting rails, is 0.52 times the speed of the moving rod, which is 1.8, gives an EMF of approximately 0.75 volts. And then from Ohm's law, the current is equal to the EMF divided by the resistance, 0.75 divided by 3, which is 0.25 amps. In Part B, calculate the magnitude of the force required to pull the rod to the right with constant speed. Because if you went back to Part A and actually figured out the direction of the current, it didn't ask you to do that, but to figure out the direction, you would see that because the area is getting bigger, it would induce a magnetic field in the opposite direction, which is out of the page. So pointing your fingers out of the page, your thumb is pointing counterclockwise. So if you think of current going counterclockwise around here, that means in the actual metal rod, the current is going from the bottom to the top. So now using the second right-hand rule to figure out the direction of the force on it, if the current is going in that direction, bottom to top of the page, you put your fingers pointing that way, curl them inward toward the magnetic field, your thumb is pointing to the left. So that means there's a force acting on that rod, pulling it to the left. So you've not only got to overcome that force by pulling on it with the string, you've also got to overcome the friction force. So to draw a free body diagram of this, you could say that if that dot represents the metal rod, you have a pulling force going to the right. You have two forces opposing that. One is the magnetic force, and the other one is the frictional force. So, since you want it to move at a constant speed, that's going to be Newton's first law, which means the sum of the forces on the right, which is just the pulling force, has to equal the two forces on the left added together, the magnetic force plus the frictional force. The magnetic force is ILB, you can leave off the sign of theta because everything's perpendicular, plus the frictional force, which is mu k times the normal force, and in this case the normal force is just equal to the gravitational force, mg. So that's equal to the current, 0.25, times the L, 0.52, times the magnetic field of 0.8, plus the coefficient of kinetic friction, 0.2, times the mass of the metal rod, which was given as 0.22, times g, 9.8, and all that is equal to 0.535 newtons. For Part C, calculate the energy dissipated in the resistor in 2 seconds. So we can first figure out the power, which is I squared R, so that's 0.25 squared, times the resistance of 3, which gives you 0.1875 watts, and then the energy is just equal to power times time, so 0.1875 times the 2 seconds gives you an energy loss of 0.375 joules. In Part D, calculate the work done by pulling the rod in 2 seconds. So work is equal to the force required times the distance. We don't know the distance, but we do know the velocity and the time, so we could write this as force times v times t. The force we figured out in part B as 0.535 newtons times the speed, which is 1.8 meters per second, times the time of 2 seconds, which is equal to 1.9 joules. And then in part E, if you compare the answers to part C and D and provide an explanation for why they're equal or unequal, you can see the answer to part D, the work required to pull the string, is greater than the energy dissipated in the resistor, and the reason is because of the friction in the system, which is a non-conservative force. So the work in D is higher, the work of the string is higher because it has to provide energy to the resistor, and it has to overcome friction.